Give two reactions that show the acidic nature of phenol. Compare the acidity of phenol with that of ethanol. First, let me give you two reactions, then we will see the logic. First is very simple. You know, phenol is not very soluble in water, partially. If you take aqueous NaOH, it is highly soluble. Why? Because phenol reacts nearly entirely with NaOH to give you a salt. What? Yes. Sodium phenoxide and water. Something which reacts with a base to give you salt and water must be an acid. Yes, this is phenol, and this phenol indeed is acting as an acid. Wow, that's great. That's lovely outright. The second is a very classical test of acidity for any organic compound. Just add a piece of sodium and watch. If you have any substance like phenol and you add metallic sodium in dry ether, what happens? You get bubbles of hydrogen. And if the substance itself is a liquid, you may not even have dry ether, that's okay. But you get bubbles of hydrogen. That is a classic characteristic test which exhibits acidic nature of any organic compound. In addition, I can tell you a third test also. Phenol can turn moist blue litmus red. So yes, that also is a very classical test for acidic nature of phenol. This was the first part. Now the second part, compare the acidity of phenol with that of ethanol. Can we compare that? Yes. And how exactly? Phenol is much more acidic as compared to ethanol. Just let us take a look at ethanol. Ethanol is CH3, CH2, OH. And if I remove one H plus, I get CH3, C, H2O minus. Entire minus charge remains on the oxygen atom. There is no scope of sharing or delocalization in ethoxide ion. But if you take a look at phenoxide ion, just watch this. I have one phenoxide ion. Yes. Is it good? Yes, it's very lovely. And if you just look at what happens to the lone pair, the lone pair can actually get delocalized within the molecule like this. I can draw contributing structures. Wow. So minus charge is not localized at one place? No. The negative charge is not localized at one place. Rather, it keeps on getting delocalized, tuck, 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 like this. And you have this minus charge like this. And this can come back and give you your old lovely phenol like this, your phenoxide ion. So these are the 5 contributing structures of phenoxide ion. Minus charge is not only on oxygen, but it is also delocalized within the ring. And greater the volume on which the charge is spread, more is the stability. So phenoxide ion is much more stable than ethoxide ion, which means if conjugate base is more stable, conjugate acid has to be more acidic. This is the rule. If more stable phenoxide ion can be formed, more easily phenol can lose H plus so that it can form phenoxide ion. That means more acidic is phenol. Phenol is much more acidic as compared to ethanol.